I talk to a lot of audiophiles every year, and at times I find that they tend to think of innovation in the field as something dramatic, technologically dramatic, that is. In the case of speakers, the mind imagines new driver physics or new driver configurations. And I get it. Plasma drivers or radiastrahlers or large electrostatic panels look dramatically different and sometimes sound quite different too. And yet, such exotic concepts have made limited headway in the market, although they show tempting promise. But what if significant promise lies in another direction? Perlisten Audio asks and answers that question. Let's take a look. In this series, we're stepping back from our normal product review cycle and looking at the companies and the people who are working on the fundamental issues of audio believability. We've identified 7 of these issues, and perhaps there are more. These are tough issues and may require special thinking and research rather than progressive incremental improvement. The series tries to shed some light on the issues and on possible solutions. While I try to explain what Perlisten is up to in this video, these are my thoughts based on the explanations from the company. As always, errors are possible, or even likely, and summaries of complex technical matters inevitably do some damage, just as much as they help with understanding. I've spent many hours listening to Perlisten speakers and talking to their design team of Dan Romer, Eric Wiederholtz, and Stephen Masenik. Each conversation tends to go on for longer than expected, and eventually it dawned on me that this is because these guys have anchored their design approach in core audio science, and that they think of the science as extending, these are my words, from the microphone to the brain. This leads them to think of the loudspeaker as part of a larger technical system that includes the recording system, the source, the amplifier, the room, the ear, and the brain. That might sound like the obvious approach, but in my experience, it isn't that common. As you'll see, the specifics of their approach are also different, but you have to pay attention to the detail. The loudspeaker is a complex beast, and to simplify that complexity, I suggest that the more common model starts with the idea of the loudspeaker as an amplifier. Not literally, of course, but amplifiers have the attractive scientific quality of being treatable as a black box, as input-output devices. You send an electrical signal in to the input side, and you get a bigger version of that signal at the output terminals. If the output signal is identical to the input in every regard except magnitude, then you have a great amplifier. Job done. No pesky room reflections or Haas windows or questions about how to integrate output over various radiation angles. With speakers, we're all tempted to follow a related model. If we weren't trying to simplify, why would so many measurements be done at 1 meter on axis? We never listen at 1 meter distance. Why would so many measurements be windowed to measure only the direct acoustic output or in an anechoic chamber? We never listen anechoically. Of course, good designers have a bevy of 30 or 50 measurements that they fuse together, with each simplified measurement playing only a partial role in generating the overall picture. That fusion algorithm, however, is rarely made explicit. To be fair, my impression is that fusing those 30 or 50 measurements together into a competent model of the speaker, even as an amplifier-like input-output device, is quite challenging, and the average designer has to live in that conceptual zone, or at least has more than enough challenges to address within that zone. Understandable, and real progress has been made working in that area. But What if the conceptual model used by a designer went beyond this? I've found a few companies that seem to be on this outside the conceptual box path, and I'll be highlighting them in this series. I start there with Perlisten Audio because their team is very clear about what they're trying to do. In my experience, it seems to work well, and their work shows how unconventional outside-the-box approaches may actually appear when viewed clearly. The important point for your consideration is that I assert that a lot of audiophiles can miss the boat by confusing exotic with breakthrough. Perlisten suggests that breakthroughs are a function of the design model and the science, not simple exoticism. To clarify this, let me explain what I've come to understand as the Perlisten design model. The model starts with the observation that there are large and small problems in audio, and many of the large items involve the loudspeaker in some way. The fundamental thing here is that Perlisten's approach is to generate new designs by starting with the big problems and addressing them. This is rare. Problem number 1, bass in real rooms. Perlisten observes that probably the largest deviation from ideal sonic results happens in the bass when we look at actual systems. Just simple frequency response measurements will show plus or minus 10 dB variations below the Schroeder frequency, which is, depending on your room size, around 200 hertz, at the listening position. If you look at measurements in the time domain, you'll also see that the room resonances generate time smear that's 2 times or 4 times what you have at other frequencies. Finally, you'll note that with many speakers, the low frequency bandwidth does not extend flat to 20 hertz or even 30 hertz. But that's not all. These problems in a conventional stereo setup cannot practically be addressed. Yes, I said cannot be addressed. You can make the room mode problems better with bass traps, but most rooms simply don't have enough room for the number and size of the traps required. And most audiophiles won't accept the aesthetic or financial hit. And even then, the problem can't be fully solved with room treatment. Perlisten points out that there's a more complete and easier solution, and this is part 1 of how they approach speaker design. The solution is to assume the use of a subwoofer array. I really don't love the term subwoofer, but it's what we have. We're sort of stuck with it. What Perlisten suggests, though, is that, listen carefully, without a dispersed array of woofers, you can never solve the room mode problem. Just to take one example, every room with just a left and a right speaker will have what is known as a speaker boundary interference response dip. This is an artifact of physics. The speaker will radiate bass toward the front wall behind the speakers. It will reflect off the front wall, and the reflected wave will cancel the main wavefront at a frequency that's a function of the distance of the speaker from the wall. You can calculate what that frequency is with the formula 1125 divided by 4 times the distance in feet from the rear wall. You can move the speakers to move the dip, but the dip is there no matter what. Well, it's there until you add more woofers in different positions with different speaker boundary interference response dip frequencies. Note that you could EQ it, but EQing nulls is challenging, which brings us to our next detail. An array of woofers has another beneficial property that's part of why Perlisten assumes this architecture. Adding woofers, especially to nominally full-range main speakers, increases the headroom of the system. And basically, to smooth out the bass, we're also going to want to EQ the bass. At times, EQ will require some added headroom. With a woofer array plus the main speakers, we can have it. We'll come back to this benefit in a bit. Note that the discussion here hasn't really been about the traditional subwoofer role, which is extending bass to very low frequencies. That might be a side benefit to a degree of the woofer array, but it isn't the core of why Perlisten assumes the use of woofer arrays for music systems. Rather, the biggest problem is in the tonal accuracy from, say, 40 hertz to 120 hertz or higher, where a lot of instruments start their workday. Remember, low E on a bass guitar is 41 hertz. Kick drum is usually tuned to 50 or 60 hertz, something like that. That said, those of you who are fans of electronic music will know that synthesizers, broadly defined, are deployed musically quite frequently in the 20 to 40 hertz range. So added flat bandwidth in this range is welcome and something that's easier to do with a woofer array. Another woofer array benefit is the easier path to tuning low-frequency balance. For decades, research has indicated that a slightly rising output as frequency falls is perceptually desired by most listeners. But exactly what this slope is, and achieving it in room, and allowing some tuning while preserving imaging excellence is a tough job. A tough job made easier, especially in your specific room, by using a woofer array. Okay, that was problem number 1, and that was a big problem. But let's go on to problem number 2, spatial presentation. Once the designer has decided to use a woofer array for the range from roughly 20 hertz to 80 hertz, or maybe a little bit higher, and of course you'll be going to higher frequencies given crossover slopes, the design of the main wideband speakers can change. And Dan Romer argues this is for the better. To understand this, we need to step back and understand the problems of spatial presentation. In simple terms, the virtual image in stereo requires 2 things. First, it requires an accurate presentation to your ear brain of the level and phase information captured on the recording. This is because level and phase are the way the brain knows where to locate the performers in virtual space. This isn't just for stereo. It's how you know the direction and distance of any sound you hear. Note that the speaker output in various directions isn't what creates the core image. That is, presentation of the performers placed on a virtual stage. The second element of spatial presentation in stereo is that we don't want to send artifacts of the recorded sound to the ear brain that indicate that the music is artificially reproduced through, in our case, 2 speakers. If the ear brain detects that the source of the sound is something other than just the level and phase information on the recording for the original performer placement, it will locate the sound at the physical source, the speaker, not at the virtual performer position. Humans are quite good at detecting these problems because it's a survival capability. Thousands of years ago, you had to know where the actual lion was. And if you ran away from the reflected sound and toward the actual lion, well, your genes were not passed on to future generations. Everyone listening to this video had ancestors who passed the spatial processing test. The biggest artifact that signals your ear brain where the actual rather than virtual source is located is uneven polar response. We want the reflected sound to be like the direct sound. When, say, the lower mid-range is omnidirectional and the mid-treble is highly directional, our ears and brains consider this to be an artifact, and we use this to detect the actual source location and place the image there. Now, consider that to produce low frequencies, you need big drivers to move the air, and at high frequencies, we only want small drivers because those frequencies require accelerations that are hard for big drivers to do. On top of that, drivers tend to be omni when sound wavelengths are much bigger than the diameter of the driver, and tend to be directional when the wavelengths are smaller than the diameter. The narrowing of radiation isn't a light switch transition. As frequency rises, the wavelengths get smaller. It just happens as frequencies approach the width of the driver. So a 12-inch driver will narrow its radiation pattern above perhaps 300 hertz and be very narrow at 1100 hertz. A 5-inch driver will begin to narrow its radiation pattern at perhaps 700 hertz and be very narrow at 2800 hertz. The point is that multi-way speakers with different driver sizes, and this is close to all speakers, face the problem of creating a radiation pattern that manages the inevitable changes in polar output so that they're hard to detect. Perlisten simply point out that once the designer has assumed the use of a woofer array, the radiation problem of the main speakers is made easier to manage because smaller woofers can be used there. And smaller woofers can extend their response up to higher frequencies without becoming overly directional. On the Perlisten S7T models that I'm familiar with, Perlisten uses 6.5-inch drivers, which aren't that far from the mid-range diameter of many speakers. They use 4 such woofers so that the total radiating area is a bit larger than a single 12-inch woofer. But with the smaller diameter, they can extend the woofer range higher in frequency and with a smooth polar transition in the critical mid-range. Perlisten doesn't stop there. They recognize that even these smallish 6.5-inch drivers become directional at lower mid-range frequencies. To limit the polar response transitions, they designed a special tweeter to be able to reach down to the mid-woofer region. The tweeter array, which they call DPC, uses 3 tweeters in a very specific and advanced configuration. This allows Perlisten to get the tweeter down to frequencies well below 2000 hertz and still be capable of high output. They think of high output as something like 117 dB with low distortion. We'll come back to this. When originally conceiving this architecture, Dan realized that the polar radiation smoothness problem is often addressed primarily in the horizontal plane, but he reasoned that it would be better to address it both horizontally and vertically. So, the architecture of the midwoofers and the tweeters and the crossovers is designed to have smooth transitions in radiation in both the horizontal and vertical directions. The output isn't the same in both directions. It's more directional generally in the vertical plane. But the issue for imaging is the smoothness of the transitions, something that's very hard with asymmetric driver configurations in the vertical direction. Okay, to not completely bury the storyline, the point here isn't just that Perlisten has some interesting design concepts, but that real speaker engineering involves managing a set of decisions that require knowledge of both electromechanical science and human perceptual apparatus. Said differently, designers know how to make drivers that at 1 meter have low harmonic distortion at 80 dB. That isn't the big problem any longer. The problem is how to realistically render the level and phase information on the recording to your brain in a real room. This requires, Perlisten would say, systems engineering. Okay, but we're not done. Problem number 3 is dynamics. I said we'd come back to the issue of levels and output capability. We need to start with a point that Dan emphasizes, which is that we aren't interested in levels because we want to play music at ear bleed levels. No. What we're concerned with is the ability to reproduce musical dynamics. I've asserted that dynamics are one of the big 7 problems of audio believability. In some sense, you be the judge of the logic, we don't want high average levels. This is because of something called the stapedial reflex. Essentially, above about 85 dB average, muscles in your ear react to protect the cochlea and the tympanic membrane. This reduces the sensitivity of the ear, so raising levels is to some degree self-defeating. If we assume 75 dB average levels, we then want to know what the dynamic range of the absolute sound, our reference, is. It varies with the type of music, artist, etc., but you might want stereo that worked with many types of music. The best measurement research has been done on orchestral music in concert halls, so we can use that, noting that in theory, electronic music might be capable of even higher dynamic range, although in recorded music, this is often not the case. Researchers often quote 60 dB dynamic range as near the upper bound of what they measure. So one design rule for your stereo would be to assume symmetrical dynamics, equal quiet and loud passages from the 75 dB average. This would mean that you would want a noise floor in your room below 45 dB, try measuring it, and you would want the ability to produce greater than 105 dB peaks at the listening position. I've often used this approach for amplifier sizing. Because a typical 87 dB sensitivity speaker will require about 300 watts to produce those 105 dB peaks, you quickly find out that substantial power is needed for 75 dB average levels and good dynamics. Dan points out that to do this with low distortion also requires speakers that can do both these peak levels and produce the peaks with low distortion. This, he says, isn't a given. To take an example of To take an example that Perlisten calculated for me, using 4 8-inch woofers, the low distortion, that is under 2% max output at 20 Hz, is 100 dB in a medium-sized room. This woofer array is equivalent to 2 12-inch woofers, and we're not at the desired low distortion output peaks prescribed by research for perhaps a modest level. Now, the frequency here is very low and other conditions might not apply to you, but maybe you can see that evaluating the dynamic capability of the stereo would involve understanding the full range capability to do high peak levels. And, crucially, note that Perlisten's research shows that these dynamic distortions are most problematic in the mid-range, so the full system has to take this into account. Okay. To return to our story, this peak level capability is affected by our speaker architecture and specifically is aided by the decision to use a woofer array separate from the main speakers and a DPC array for the upper mid-range. The woofer decision also tends to reduce the demands on the amplifier for the main speakers since the woofers often bring along internal amplifiers. Leaving the main full-range amplifier with a somewhat smaller frequency band may assist in cleanly producing the needed mid-range and high-frequency dynamics. Now, problem number 4. System integration. The Perlisten team acknowledges that integrating speakers into real rooms is a challenge. On top of that, their preferred architecture adds to the complexity of setup because the consumer has a woofer array plus the main speakers to sight and blend. On the other hand, with a woofer array, speaker positioning for bass balance and speaker positioning for imaging are now somewhat independent variables, which is quite helpful. Perlisten showed me a prototype of an integration box they're building for release in 2026. The box addresses several issues. Time alignment of the woofer array and the main speakers, something that's especially challenging because woofers tend to be slower, and thus the main speakers must be delayed if we're to avoid having to place the woofers in front of the main speakers, something that's generally difficult, impossible, or undesirable, or all three. Next, we need to EQ the woofers, the crossover, and the main speakers so that the woofer array can fill in dips in the main output between the modal frequencies and the SBIR dip. Modal frequencies can also be trimmed with EQ if needed, and that's very frequently needed. Then we want multiple woofer outputs, 4 to be precise, allowing independent control of elements in the woofer array because distributing the woofers has benefits for the task of smoothing total output. Then, such a box needs to control the basic tilt of the overall resulting response curve. This is something most listeners want, but which most systems only allow via positioning and ancillary gear like switching amplifiers to change frequency balance. Perlisten allows this to be directly controlled and allows for multiple settings with presets for different recording types. It's important to emphasize that the issues addressed by this control system may sound like they are a byproduct of the woofer array architecture, but that mostly these are issues that exist in every or almost every standard stereo system. Note that another way to accomplish these goals is with Trinnov processing and a waveforming woofer array. The new Trinnov CI processor is ideal for music systems and will report on the results with that soon. The Perlisten control box is designed to reduce the price point of a well-integrated system, both because the box will be priced below the Trinnov CI and because Trinnov requires a minimum of 6 woofers. It's also important to note that providing this control means the use of DSP. This is a profane word in some circles, but if this video has been about anything, it's been about the significance of system-level implementation decisions. My experience is that it's worth considering the many ways in which the Perlisten architecture is different and then taking the step to wondering if you simply don't have experience that allows you to predict the results of such a different approach. With that in mind, you'd want to check it out. Okay, then how about demo time? Well, I did check it out. Perlisten demonstrated a system using the S7T Black Edition, a full redesign at a higher price to improve on the excellent S7T I've reviewed. They use these as main speakers with 2 D8IS subs. Those are 6 woofer systems each. The bass balance, accurate instrumental tonality, bass power, and bandwidth, and overall system dynamics were excellent. The sound was a testimony to the ability of the architecture to refine bass quality and the new control box to mitigate the potential issues with setup. Honestly, you could have told me that the subs were turned off, so complete was the sense of timing and frequency integration. Now, this is a system I'm not familiar with, in a room I'm not familiar with, and so again, I suggest you do your own test drive. All right, this has been a long one. I think worth it, but a long one. Let's wrap up. Speaker design is hard. We know this because we measure a lot of speakers, and we listen to even more, and they vary rather significantly in sound quality. They can't all be right, although some of the variation comes from making different trade-offs. But it often isn't clear exactly why they differ. One suspects that some of the differences come from how different designers conceive of the problems they're trying to solve. Perlisten has, to my mind, an impressively complete view of the problems of audio believability and the solutions. In my humble opinion, this is a company to watch. I hope you've enjoyed this profile of the speaker design logic of Perlisten Audio. Thanks for watching, and we hope to see you again soon.